Lenz's law is a convenient alternative method for determining the sign or direction of an induced EMF or current, or the direction of the associated non-electrostatic field. It always gives the same results as the sign rules we have introduced for the electromotive force and the flux by dt in connection with Faraday's law, but it's often easier to use. In fact, it's a lot easier to use. I mean, the last few examples where I was showing the minus sign with the Faraday's law, it's very confusing when you first come across that, but if you use Lenz's law, it just makes more sense, and it's much more intuitive. Once you see Lenz's law, you won't worry too much about that sign convention, because Lenz's law takes care of it all really quite nicely. It's a nice, simple little thing to make you remember. It helps us gain intuitive understanding of various induction phenomena. Actually, it's very useful. So Lenz's law states the following: the direction of an induced current is such as to oppose the cause that's producing it. So that's it really, that's the main thing to remember. The cause of the current may be the motion of a conductor in a magnetic field, or the change of flux through a stationary circuit. In order to have an induced current, we must have a closed circuit. If a conductor does not form a closed circuit, then we mentally complete the circuit between the ends of the conductor and use Lenz's law to determine the direction of the current. The polarity of the ends of the open circuit conductor may then be deduced. Here, for example, a moving metal conductor in a magnetic, so we're looking at this, in a magnetic field will induce a current whose direction of the resultant sideways force via the magnetic field is in opposition to the metal's direction of movement. The motion of the metal conductor is therefore opposed. So what we're saying is there is some force that is pushing this bar over, and when it's pushing the bar over, it's actually increasing the flux line. So you can see this area now, extra flux. Well, of course, when you move that bar over, you want to oppose that change. To try and make the flux the same, it's got to try and push a force on the other way. So what we do is, if we just use the right hand rule again, we put our fingers in the direction of the magnetic field, and our palm then points in the force that we want to oppose the force. If we're pushing this way, then we will oppose that change, and our thumb then indicates the direction that the current will flow in. The induced EMF will be in this direction. In this case, we're pushing the magnet in very fast in this direction. We're increasing the flux. Now, that wants to keep the flux the way it was. It wants to oppose the increase in flux. So how's it going to impose the increase in flux? Well, the way we can work it out is if we put our fingers around that to oppose this increasing flux. So we want a flux that goes that way. Then our thumb again will point in the direction of the resultant EMF. So the EMF will be in that direction, therefore a current will flow around here. And then, of course, in the other case, if we're pulling this magnet away, so now what we're doing is we're pulling the magnet away from this ring, so we're decreasing the flux. To oppose this flux decreasing, we want to put our fingers around there, so we want the flux to be going in this direction, which opposes that direction. So if we put our fingers around there, then we can see that our thumb then in that case is going to be pointing down. Okay, so you can see to oppose that flux decrease, we need to produce our own little flux going in the opposite direction. That means the induced EMF will be going that direction. So really, that Lenz's law enables us to formulate Faraday's law really easily by using this idea of opposing whatever the force is that's being produced to change the flux, etc. As long as we oppose that, then we'll get the direction of the induced EMF. So that's a really useful way. So Lenz's law is really a simple way of visualizing all this, and it's just much easier, I think.